Now we will make the derivation of the principal component analysis formula. So basically, we need to go back. That's something that you saw before, I think twice, in fact. So we see it again, the Lagrange multipliers. So the idea of Lagrange multipliers is to do some optimization under constraints. So basically, for example, we want to maximize function f under the constraint that function g is equal to 0. This is the constraint. And the point is that we have some parameter lambda not equal to 0 that allow us to get something like this. There is a parameter such that the gradient of f, the derivative of f plus lambda, the derivative of g is equal to 0. And as such, the corresponding equation with the Lagrange multiplier is something like that. So we get the equation with the Lagrange multiplier, which is equal to f plus lambda g. And as such, we are obtaining the maximum obtained by finding that the gradient of big L is equal to 0. And this gradient is basically, this gradient of big L is equal to 0 is equal to correspond to that, given what we have here. If we are only interested by x, we can eliminate the lambda without having to evaluate it. So we put it there, we make the developments in terms of equations, but in the end, we can get rid of that lambda. It is not that useful after the fact. It's really a useful things to use here in terms of our formulation. So an example of that is to maximize the function 1 minus x1 square minus x2 square. So this is what we want to maximize. And we have the constraint that x1 plus x2 minus 1 is equal to 0. So these are, so the f is the function to optimize, g is the constraint on that. The formulation with the Lagrange multiplier leads us to something like this. So it's basically the function f here plus lambda function g. When we are computing the derivatives, we compute this according to x1, x2, and lambda here, because we also have lambda. So derivative according to x1 is that thing, according to x2 is that thing, according to lambda is that thing. What is great here is that we just have 3 equations, 3 unknown. So we need to solve that system equation, which is relatively straightforward. We have something like x1 is equal to 0.5, x2 is equal to 0.5, and lambda is equal to 1. This is our new, our solution that is optimizing this function. So in fact, visually speaking, this is what it means. So the function f basically is maximized at 0, 0. So when we are on the origin, this is the peak where we have the maximum value, which is basically 1. All this will be equal to 0. So as we go away from that, we are looking at the Euclidean distance that we want to minimize to the origin. And as such, you see the dashed line here, this black dashed line here is function g, is our constraint. And our constraint states us that we need to stay on that line. We cannot move elsewhere. So by staying on that line, I would say what will be the point with the minimum distance to the origin? That's that point here. That's the point at 0.5, 0.5. So that's the point where we are on the line while still minimizing the distance, because we see with the contour curve here that, we are only further away. So this is really the point where we are the closest possible to the origin here. So let's now go back to the PCA derivation. We will define the first component W1 as the direction of the main variance. So we say, okay, we have W1, this is the direction of the main variance, the principal component, principal variance. Now let's define Z1 as equal to W1 transpose X. So only the direction here is important. We don't care much about the magnitude. So we can constrain basically the vector to be a unit vector of length 1. So now we could just state that, okay, our covariance is equal to the big matrix big sigma in bold. Then the variance here after this transformation of Z. So we say the covariance of X is that. Then the variance of Z1 here, which is obtained from that, is equal to W1 transpose big sigma W1. And then we just put in the expectation of W transpose X, which is basically the expectation of Z1, which is equal to that thing. And if we simplify it, we get something like that. So the expectation is W transpose mu. And the variance here, if we use the equation of the variance, which corresponds to that, we can develop this into something different. We just kind of expand it here. And then we simplify it in some way. So we've got that thing. And then we've got, so given that the expectation is based on the X, we don't care about the W. So the expectation is that thing here. And basically it boils down to this thing correspond to the covariance. So basically the variance for W transpose X, which is basically Z1, is equal to that thing. This is what we stated here. Well, now let's look at the vector W1, which maximize the variance Z1 with the constraint that we have a unit vector here. So W1 transpose W1 is equal to 1. So the resolution by Lagrange method tell us that, okay, let's use this here. We have, we want to maximize the variance, which is that thing, variance of Z1. So this is the one we want to maximize minus alpha, this thing which corresponds to that constraint. So now we have as derivative that thing. So basically, if we just move this thing, okay, let's move it there, let's move it there, and we don't care about the two here. We have that thing. We have epsilon, no, sigma W1 equal at alpha W1. By definition, you know, this is going back to the basics of linear algebra. The sigma W1 equal to alpha W1 is true when W1 is an eigenvector of covariance matrix, big sigma here, and that alpha is the associated eigenvalue of W. So this is a definition, common definition of linear algebra. I refer you to your notes from that course. So basically, we're starting from that. We can see that we want to choose the eigenvector with the largest eigenvalue. So basically, we say, okay, by making an analysis of eigenvector, eigenvalues extraction of of this thing here, of our covariance matrix here, basically, we will be able to obtain the values corresponding to our principal component. So the variance here, given that, so with this thing, you know, knowing this thing here, we are able to simplify this by that and make this corresponding to alpha, given that W1 transpose W is unit. So the variance basically of our transform space, which is W1 transpose X, is equal to alpha, which should be basically the largest eigenvalues in our decomposition of the covariance matrix. Now, if we look at the second principal component here, we just need to look at the second vector W2 that maximizes variance of Z2. So first constraint, W2 is unitary. So we just say it there like this. We see, okay, we have a unit vector. Second constraint is that W2 is orthogonal to W1. That means that when we are making W2 transpose W1, it's equal to 0. These are completely orthogonal, because we want it to be in another direction. So resolution by Lagrange methods give us that thing. So we have two constraints. So we just put like one alpha, which is about this first constraint. And then we have a beta that is corresponding to that second constraint. So the derivative leads us to that thing here directly. And if we move things a little around, we get something like this thing. So we have 2 W1 transpose sigma W2 minus 2 alpha W1 transpose W2 minus beta W1 transpose W1, all this equal to 0. Given that we have this here, then we can see things like W1 transpose W2 is equal, this thing is equal to that thing, just inversing W1, W2 doesn't change anything. And from that, we know that this thing should be equal to lambda 1 W2. And all this should be equal to 0. Given this, so we have this thing. So we say that this thing corresponds to that thing here. So given all this, we know that by definition, W1, W2 transpose is equal to 0. So we have this equal to 0. And if we develop further here with this equation, put it in there, we have something like this thing is equal to that thing is equal to 0. So we simplify basically things by saying that so 2 sigma W2 minus 2 alpha W2 minus beta W1 is equal to 0. So with this results, it implies that sigma W2 is equal to alpha W2. So that implies that W2 is also an eigenvector of our covariance matrix. So that's kind of important results. Since we want to maximize the variance over Z2, which is equivalent to W2 transpose X, we choose the eigenvector associated with the second largest eigenvalue. We just set the alpha here as lambda 2. And we proceed that way for the other dimensions. We continue to choose a different Wi as the eigenvector associated to the largest eigenvalues remaining. So basically, we can simply sort the eigenvalues in decreasing order and using the associated vector in the right way to build up our base. Rotation matrix is defined as this thing. So basically, W is equal to W1, W2 up to WK, and contain a key inferior to the first eigenvectors. So the one with the largest eigenvalue. So if we just keep the K first one from the set of D possible eigenvectors, we choose the K first one associated to the biggest lambdas, the one with the biggest eigenvalues. Additional properties of that is that since the covariance matrix is symmetric, eigenvectors are orthogonal. Since Wi is unitary, they form an orthonormal base, basically. And since covariance matrix is defined as positive, all eigenvalues are non-zero. If we have something that is not positive, if the sigma is not positive, we have some dependencies between some components. That means that these will have a possibly zero value, the eigenvalues, especially when one is dependent from the other. Otherwise, the rank of sigma gives a number of non-zero eigenvalues, and this is quite useful when we are making our analysis. So basically, if we look back again at our example, which is centered here on the mu, this is the mean value of our multivariate Gaussian distribution. And we have the blue curve here as a contour plot at a given distance from the origin, from the center of the distribution. We can see basically that in the direction of the biggest variance, we have a value corresponding to square root of lambda 1, so which corresponds basically to some kind of standard deviation, but in that specific direction. And likewise, the other direction is given by square root of lambda 2. So when we apply the linear transformation, this is what we do. Basically, we center on the origin and we just reshift everything to remove translation.